So, we started discussing about two-dimensional NMR spectroscopy in the last class. We introduced the general concept in a qualitative manner. We said this principle is like this, that you have a time axis like this and you divide the time into two different segments, and which in multiple segments we call the first one as the preparation period, and then you have the evolution, we call it evolution and labeled it as T1 period. Then we had the so called mixing here, and then we had this detection, and which is where we actually collect our FIDs, and this is the time period T2. So, we collect a series of FIDs incrementing the time T1 from one experiment to another experiment. Therefore, this will result in a two-dimensional data body T1, T2, and you do a two-dimensional Fourier transformation. This will generate a two-dimensional spectrum which we call as F1, F2, or sometimes people also use this as omega 1, omega 2, it does not matter, either way it is the same thing. You need a two-dimensional Fourier transformation. So, the concept which you have to be clear is that this is segmentation of the time axis. So, the idea can be extended further to multiple dimensions as well. You are introducing one evolution time T1, you can introduce other evolution times, you can use 2, 3, 4, 5 etc. Then accordingly will generate various kinds of evolution times. So, we took a particular examples of 2D spectra where we talked about the 2D J resolved, okay, 2D J resolved spectroscopy, and there along the two frequency axis we had one axis we had the J, other axis we had the delta. So, this became a 2D separation experiment, the two coupling constant is on one axis and the chemical shift is on the other axis. And we are going to go into other kinds of 2D experiments, and those are the correlation experiments. However, so correlation experiments, before we actually embark onto the correlation experiments, we need to clarify some of the other concepts and need to define certain terms. Some definitions we have to give, because this will be required for all our future discussions. For all our future discussion, what sort of a magnetization, how do we generate various kinds of magnetizations, how do we generate different kind of information in different spectra. So, therefore, here we will have to make a slight digression and define certain terms. Okay. So, some definitions we will give here. Some definitions, because these are the terms which we will be using all the time. So, in a generalized multipulse experiment, you have various kinds of evolution periods, preparation periods as I mentioned here, and there is what happens is you start from initial magnetization which is here, and the magnetization flows through these various time periods. This may be T1, T2, T3 etc. So, the magnetization flows, if I want to use a different color for the magnetization, it will flow through this and ultimately we collect the data. So, this is called as the magnetization transfer. Magnetization transfer or magnetization flow. Okay. So, it goes from one state to another, from one T1 period to T2 period to the T3 period and so on and so forth. So, here magnetization flow is something which one has to understand, and that determines what magnetization is present in what time period, determines what is the information in that time period. When you Fourier transform it in a multidimensional way, the information that is present in the T1 will appear as F1, what is present in T2 will appear as F2, what is present in T3 will appear as F3 and so on and so forth. And these various time separations here, which are there can be various kinds of mixing periods here which will allow transfer of magnetization. That is why we are talking about magnetization flow. Magnetization terms will have to be defined here. We have to define certain types of magnetizations, okay. That is what we will do here. So, let us keep those definitions here now. Let us say we have the term called IKZ. IKZ implies Z magnetization of spin K, okay, and this has to do with the populations of the levels populations of the levels of K spin. Which will cause K spin transitions. Okay. Then let us say I have IKX, let us say this means X magnetization or the transverse magnetization, X magnetization of spin K, and we are talking about spin half systems here. Okay. For all of these, let us say we are talking about spin half systems, all K, L, etc., whatever label we use. I have used as the label K, that is to identify the spin K. I can use it L, M, P, Q, R, whatever, they all indicate different spins and they are all spin half systems. Okay. So therefore, and we need two different symbols here. Similarly, if you have IKY, IKY would imply Y magnetization. Okay. Now among these, what is it that we observe? It is a transverse magnetization, right. When we measure the transverse magnetization. So we measure transverse magnetization always, measure transverse magnetization. And that is IKX or IKY. IKZ is not observable, okay, because you have to convert this Z magnetization into the transverse plane, bring it to the transverse plane, because your detector is in the transverse plane, therefore you measure the transverse magnetization. Now if I measure the IKX term, if I measure the IKX and after Fourier transformation etc., you get the time domain signal, you get the FID for this FID, and if you do Fourier transformation, you generate a, suppose it is a spin which is coupled to another spin, suppose it is coupled to another spin, we will generate two components like this. This is the doublet of K. If it is coupled to some other spin like L, okay, it will produce an in phase, this is called as in phase doublet, in phase signal. Similarly, you can write for IKY, IKY will give you antiphase terms IKY, FID, and this may generate you a dispersive signal. This is in phase dispersive. You can choose either way, I mean depends upon where your detector is. If I choose IKX to produce this absorptive phase, then the IKY will produce me dispersive in phase and vice versa. Suppose I put the detector along the y axis and I measure the y magnetization, I get absorptive signals for the IKY magnetization and IKX will give me dispersive signal. So these are interchangeable. Okay. So this is one set of terms which we will always use, IKX, IKY, ILZ, and when we have other kinds of, what are the other kinds of magnetization terms? Let me define few other types of magnetization terms. So we also will come across terms something like this, 2 times IKX ILZ, and this is called as antiphase magnetization of K, which is antiphase with respect to spin L, antiphase with respect to spin L. What does that mean? What does that mean? So if I take term like this, 2 IKX ILZ, now I do, this is evolves during the generate an FID from here, because the FID generate means this has to evolve, various kinds of evolutions will happen, and then of course after you do a FID, then I do a Fourier transformation and collect the signal. This will generate the same two lines, but they will have appearance like this. So this is called as antiphase magnetization. Okay. So IKX ILZ, this kind of a magnetization, this is the magnetization term, and which this evolves in the FID, free induction decay, because there is a J evolution that will happen there, and after you do Fourier transformation of the resultant magnetization, that is will produce you a spectrum which is like this. So, these are called as antiphase signals. Same will apply for to IKY ILZ as well. IKY ILZ, or suppose I take ILX IKZ, suppose I do this to ILX IZ. What does this mean? This will mean the same sort of a terminal we will get, but this is antiphase magnetization of spin L. Okay, this is spin L, which is antiphase with respect to spin K. See, the Kz indicates that it is with respect to spin K, and Lx means it is X magnetization. This is X antiphase magnetization. Okay. Similarly, I can also have 2I Ly IKZ. This will be Y magnetization of spin L, antiphase with respect to spin K. Okay. So, these are the kinds of terms which you will get when we are actually considering a series of transfers from one time period to another time period during the mixing periods. When you do mixing times, during the mixing time we generate transfers from one spin to another spin. See, if I go from Kx to, let us say, 2KxLy, 2KxLz to LXKZ, it would mean that I have transferred from the K spin to the L spin. So, this sort of transfers will happen when you are doing this mixing periods. During the mixing times, this sort of transfers will happen. Okay, that is why it is important to understand these terminologies, how this will happen. Okay. So, and there will be other kinds of terms, and all of these are, so all of these are called single quantum transitions also. So, I will have to explain that in this context using an energy level diagram there. Suppose I am taking a 2 spin system. So, then I will have here, these are all, let us say, alpha alpha, alpha beta, beta alpha and beta beta for the 2 spin system. So, I will have transitions here, transitions here, transitions here, transitions here, and all of these are delta m is equal to plus minus 1. Therefore, these are called as single quantum transitions or coherences. And notice, when I say transitions and coherences, the transverse magnetization always represents the phase coherence between spins, whereas the Z magnetization represents populations, as I mentioned earlier. The transitions, the transverse magnetization refers to single quantum coherences. These are all single quantum, because what is m value here? M value here is 1.0, m is 1.0, here it is 0, here it is 0, here it is minus 1. Therefore, the transitions which I have indicated there, these are all delta m is equal to plus minus 1. Therefore, these are single quantums. Now, what are the other transitions possible? There are other transitions possible. You can have a transition here, and this is dq, double quantum coherence, because the delta m is equal to 2.0. These are not directly observable. Of course, with selection rules, when we consider, the double quantums are not directly observable, but these will be created in the course of your pathway magnetization flow. This kind of terms will also be created, coherences will be created. And then you also have a third kind of a thing possible. Let me see here, and this is ZQ, 0 quantum. So, ZQ is called 0 quantum coherence, and dq is called double quantum coherence. So, during the magnetization flow such kind of magnetization terms will be created. Okay. How do we know these ones? What are the kinds of magnetization terms which represent this? Okay. This is what we will see now here. You can have things such as 2ikxily or 2ikyilx or 2ikxilx or 2ikyily. This kind of terms indicate, these indicate mixtures of double quantum plus 0 quantum coherences. A combination of these can create pure double quantum or pure 0 quantum. Okay. Combinations of these can generate pure dq or pure zq. Okay. So, for example 2ikxily, for example ikxily plus 2ikyilx, this represents pure dq, this represents a pure dq. So, similarly I can also make I can also make 2ikxily minus 2ikyilx, that will represent a 0 quantum. So, such kind of combinations are possible. You will generate pure double quantum or 0 quantum or mixtures of double quantum 0 quantums and double quantum or in general multiple quantums, or in general these are called multiple quantum coherences. You can also have a triple quantum coherences, but these are not directly observable. When you put detector, these are not directly observable in a detector and they have to be converted into single quantum coherences for detection, but these can appear in your transfer pathway. So, these are not directly measurable, in the detector systems, but they can appear in the magnetization flow. Okay. So, therefore, when you are having multiple experiments, various kinds of transfers at various places, all these kinds of terms will appear. So, and we are going to use this in all these multidimensional and SMRM experiments which we will discuss, as various kinds of correlation experiments which I mentioned to you, they will come across all of these kinds of terms, and therefore it is important to understand what we are talking about here. So, in the general scheme which you have various kinds of teams here, you can have single quantums here, you can have double quantums here or 0 quantums there, or you can have Z magnetization, you can have pure double quantum. I am just randomly writing here what all things can happen, okay, coherences, and here you have Z magnetization. So, these are the pathway, this is the pathway along the time, and when you detect here, this will be pure, this will be single quantum coherences only. You can detect only single quantum coherences, and here it, because this is the selection rule, delta m is equal to plus minus 1, only that thing can be detected, but these ones can appear anywhere in the pathway. So, this actually represents the pathway of flow. Pathway of flow of magnetization. Okay. So therefore, one can design various kinds of experiments at what you want to have in a particular time period. I may want to have single quantums here, I may not want to have single quantums there, I want to have double quantums there, I might want to have, I can delete some of those ones, how to manipulate those ones. This is the thing which actually generates a whole lot of experimental schemes which are required for generating a specific type of information in your spectra, and that is what is the power of this multidimensional spectroscopy. You can use different kinds of nuclei, generate different kinds of coherences in this experiment. So and then I will have terms such as 2ikz, ilz. I will also have such kind of terms, and this is called as 2-spin order, 2-spin ZZ order. This can be converted into single quantum or double quantum. This can be converted to SQC or DQC or ZQC. All such kind of terms can be there. This is so far as 2 spins are concerned. Now let us consider what kind of things can happen for 3 spins. 3 spins, again I can have, let us say these spins are K, L, M. Suppose I have 3 spins, then I can have terms like IKX, individual ones ILX, IMX. These are all M, K, L, M spin magnetizations. K, L, M individually X magnetizations of, these are all X magnetizations of K, L, M spins. Okay. Alright. So, and the two spin terms will also be available. You can make combinations of 2ikx ILZ or 2ikx IMZ and so on and so forth. So, there will be 2 spin terms also there. Now, there can be 3 spin terms. 3 spin terms are like, suppose I have things like that, 24 ikx ILY IMZ. Suppose I have a term like this, I get a term magnetization in the pathway, I get things like that. What does this imply? This will imply dq plus zq of k and L spins antiphase with respect to M spin. Note whichever one is Z, it is antiphase with respect to M spin. So, this will lead to a particular kind of a pattern in your final spectrum when you generate it. Or that I can also have things like this 4 IKX, ILZ, IMZ. So, now I have 2 Z parts, transverse is only one, transverse is only with respect to the K spin, but I will have the Z with respect to L and M. So, this will be single quantum of K antiphase, single quantum what? Transverse magnetization, X spin, this is X magnetization, antiphase with respect to both L and M spins. These will generate different kind of terms when you actually do a measurement. So, if you have such a kind of a term, let us take for example IKX ILZ. Now, in the 3 spin system, how will the IKX look like? So, then the 3 spin system is like this. I have the K spin, L spin, M spin, and there is a J for each one of those, J1, J2, J3, let us say if I have those. How will the IKX look like after this generates a FID, and then you measure take the FT, and this will give me for the K, I am only writing for the K because it is the K spin. So, the K spin will give me 4 lines, which is a doublet of a doublet, right, because it is 2 couplings J1 and J3 couplings. this will generate a doublet of a doublet. So, if these coupling constants are not equal, then it will be doublet of a doublet. Okay. In the same one, suppose I have a term which is like this 2 IKX ILZ. So, what it will generate to me? This term in the FID, and then you do FT, and this will produce spectrum like this. In the spectrum it will appear like this 2 IKX ILZ. Notice here this repeats here, positive negative positive negative. So, it repeats. This is called as, it is antiphase with respect to the L spin. Okay. Now suppose I have this kind of a term 4 IKX ILZ IMZ, and this generates an FID, and then I have the FT, and this will produce a pattern like this after Fourier transformation. Now you see this is positive negative, this came from the antiphase with respect to the L spin, and then again now negative of this. So, therefore, positive negative negative positive. Okay. So, therefore, for this is plus minus plus minus, and here I have plus minus minus plus. So, 2 negatives. So, one negative coming from the K to L and the second negative coming from K to M. So, therefore, you will get this kinds of a pattern. So, this is the doubly antiphase magnetization. Therefore, this is called as doubly antiphase. Antiphase magnetization. Okay. Okay. So, alright, then let me also write one more term which is to complete the story here, IKX, ILY, IMX, or any combinations of those. If I write like this, these are called as triple quantum coherences. Once again, this will not be directly observable, these will have to be converted into single quantum coherences before actually you can observe, and then we will generate the various kinds of spectral features as I indicated in different things like this. Okay. So, we will be dealing with such kind of magnetization transfer pathways as we go into the multidimensional NMR experiments. In fact, this is when we want to talk about the COSY and the NOSYs and things like that, these are required. That is why I introduced these ones beforehand, so that we will have no difficulty in understanding these kind of situations. Okay. So, alright. So, then I think we can stop here, and we go into the next phase, into the next class.